in the next class. So we
Okay.
studied that when we have torque across any electric field, means basically a dipole is present in an electric field. The dipole tends to rotate along the direction of electric field. This is due to the torque that is present. So the formula of torque was P cross E, which is PE sine theta. Now, there is what was all this that we studied yesterday? It was basically the dipole in uniform electric field. See, for us, the whole time electric field was constant here. E was here, E was here, the electric field was constant. And if you notice, when electric field is constant, it is equidistant also from each other. So these we'll see in the properties. So look, what if this electric field is not uniform? Just one more part that is left. And what if this electric field is not uniform? So this is the second question that was left. If it's not uniform, no, see, like you are getting E1 here, electric field lines are closer, then there are a lot of spaces, and then you have E2. So in such a case, remember, first you tell me, Basmi, one thing. If this is plus Q, here charge is even, what will be the force acting here? Force that will be acting.
Force towards the electric field.
Value of force, formula.
Uh, K Q square by R square.
Force. I'm asking the force. F. E is there. Q is there.
Oh, like that. E is equal to F by Q. You use that formula. So F will be equal to EQ.
Exactly. So if we are talking about the force, force will be, this is a positive charge. It will be in the direction of electric field. And the value will be plus Q E1. For the negative charge, this will be in the opposite direction of electric field. And the value of this will be minus Q E2, the full value I've written. Now, in the previous part, if you remember yesterday, the portion which we did, the net force which we calculated, it came 0 because plus QE minus QE, they got cancelled on both sides. So here, look, when you are calculating the net force, so net force will be equal to, one will be this plus QE1, second will be minus QE2, and this won't be 0, means this will have some value. So what's the motion of a dipole in non-uniform electric field? It is not an equilibrium, right? There will be a net force. We will get a net force, means dipole will move because there will be a force acting. There will be translational motion of the dipole. Okay, it won't be like your previous case because that time net force was 0, so it was an equilibrium, in complete equilibrium. And for torque also, torque you will calculate. First torque will become PE1 sine theta 1. Second torque will be PE2 sine theta 2. So rotational motion will also be there, not only translational, but you will have rotational motion will also be there. So if a question comes, explain the motion of dipole or movement of dipole in the uniform electric field. So in uniform, you are going to mention the above case which we did. And for non-uniform, this is your answer. Okay, write down this, then we'll start with something next.
Ma'am, I'm done.
Written?
Yes, ma'am.
Okay. Now, see, all these things were when this torque was related to your electric field. So that's why we discussed this first. Now let's come to one important topic. If a charged particle is there in external electric field, questions do come from it, and this relates with your class 11th portion. So stay alert here because this part is a little bit not, see, it's not just confined with your 12th portion. So it will involve a little bit of your 11th. So when a charged particle is there in external electric field, it's present. First of all, we know the force will be F is plus Q E. So since we have done this part, this I am doing it quickly. And remember, as I was mentioning yesterday also, that when you have a positive charge, if a positive charge is present, its direction will always be along the electric field. If electric field is towards the right, your charge will also move towards the right, like this. But if it reverses, why are we studying this? Why is it important? Because in the questions you have to see a proton is mentioned, an electron is mentioned, which particle is mentioned. So for that you have to be very careful. And if there is a negative charge particle and it is put in electric field which is opposite, so this direction will be exactly the opposite. The direction of force will be in the opposite direction. So here the force F will be minus Q into E. Minus Q into E is telling you the full vector with the direction. Minus sign basically tells the direction of force. When you are asked to calculate the magnitude, it will only be QE. And do not forget this formula. This formula QF is equal to QE is very important because not in this chapter only. In the rest of the chapters also QE will be used. In your magnetism, you specifically have a topic that involves this. So just have it in your mind to not to forget it. Now, there's a very easy question to start with. Then we'll come to the kinds of questions that come. This says a charged particle of plus 2 coulomb is placed in electric field of 5 Newton per coulomb as shown. Figure is also mentioned and we need to calculate the forces. So see, charged particle here is given as plus 2 coulomb. Electric field is also given, yeah, 5 Newton per coulomb. So force F is equal to Q. E will be the force. So this is easy. 2 into 5 is 10 Newton. But we need to mention the direction also. So since it's a positive charge, where should be the direction of force?
It's the same direction of electric field.
And where is the direction of electric field?
I J cap.
J cap, correct. So this will be J cap. That's it, right? Similarly, if I reverse this, means if I change the charge as negative, I take Q as minus 2 coulomb and electric field is still 5 Newton per coulomb. So force's magnitude will still be QE. That is, we'll write 2 into 5 is 10 only. But direction, see, 10 Newton is there, but this is a negative charge. So we should write
Minus J cap.
minus J cap. Exactly. This will be minus J cap. You can use downwards and all. That is also fine. Then we'll come to these kinds of questions. First, you write down this from here. Make the heading as this, charge particle in external electric field.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, I'm done.
See, Basmi, this question says a proton and an electron are placed at rest near positive and negative plates. Means you have to check positive and negative plates are mentioned in the diagram. So basically, these are usually capacitor plates that are given from your capacitor chapter also. But without that, these separate questions can also come. So just plates are present with the charges. Now are placed at rest near positive and negative plates. So it means a proton and an electron, they are placed at rest near, proton is near positive and electron is near the negative. That's what it is saying. You have to calculate the time taken by proton and electron to reach the opposite plate. See, proton is positive. It will be attracted towards the negative plate. Electron is negative. It will be attracted towards the positive plate. So if this is the case when they are traveling through this distance, let's say this distance is small d. If this is the distance small d, they have to cover these distances. It is saying what other times, right? And it is saying calculate time taken by electron and proton to reach opposite plates. You are going to use the method. See, when electron is asked to move or when proton is asked to move, what's the equation of motion? What are the equations of motions?
V is equal to U plus AT.
Yes.
And then 2AS is equal to V square minus U square.
Yes,
and
one more.
then S is equal to UT plus half AT square.
Correct. So you have to use these equations only in order to write down the time, because from where will you get this time? Okay. Now let's say the length of this plate is some L. Let's say the length of this plate is some L. Now see what, or even you can avoid the length, because right now the movement is across the y-axis only. Avoid the length. Let's leave it. We have taken the distance d, that is enough. Now for the electron, for the proton, let's start with the proton. For the proton. Yeah, Basmi, what is the distance that it has to cover?
It should cover d distance.
How much?
D.
D, right. Distance will be D, that is fixed. What will be U?
U would be P.
How
Proton.
much? For proton, what will be the value of U?
1.6 into 10 raised to minus 19.
What
It will
is
be
U?
charged. It's the initial amount.
Initial velocity.
Sorry, velocity.
So what will be the initial velocity? Look at the
Oh, it's
question.
at
That's why I've scrolled.
oh, it's at rest. 0.
Exactly. It's at rest, na? So they are placed at rest, means U will be 0. Now, for acceleration, what we have to do for the calculation of acceleration, look, F is equal to, what's the charge on proton?
Charge on proton is 1.6 into 10 raised to minus 19.
Right, that is the electronic charge only, E. And let's say the electric field is E. Now, from the second law of motion, F is equal to ma. So acceleration will be force by mass. Means acceleration will be E by m. So here the acceleration will be E divided by mp. mp means mass of proton. Okay. T we don't know, that we have to calculate. So look, which equation should be suitable according to you?
F is equal to ut plus half at square.
Correct. S is equal to ut plus half at square. If you put the value, this is 0. Ut is 0. We get the answer very quickly. Half. Acceleration is E by mp t square. So what do you require to calculate? You require the value of t. T will be 2 dmp divided by E into E under root. Similarly, for electron, T will be equal to 2 dme E by EE under root. This you will write the steps by yourself. Answer will be this only. Now, there is one more type of question that comes from this only. This question. Instead of asking you directly the time, it can ask you, because these questions have come. They can ask you, one question was there which came in your board exams. If this was a race where electron and protons are moving, who will win the race? Like this. So basically you have to find out which element will have a higher time to reach the final point, which will take a lesser time. So what do you think?
Both will take the same time, right?
Same time. Same time. No, see, time, if you see 2DEE is common for both of it, but time is depending on root MP. Means time is depending on the mass, and mass is not the same. Mass of proton is greater than mass of electron. So time of proton will also be greater than time of electron. Means electron, if time of proton is more, proton takes a lot of time to reach. Electron will reach fast. Electron will reach faster.
Oh.
So this can be a modification that can be asked. Okay.
Okay, ma'am.
All right. Please write down this thing.
Ma'am, I'm done.
Done?
Yes, ma'am.
Okay, let's continue. See, this is saying predict the magnitude and direction of electric field so that Q is in equilibrium. This is basically the figure is missing. Let me tell you the figure. This is the charge. And see, it is saying magnitude and direction of electric field so that Q is in equilibrium. When we say Q is in equilibrium means the net force on the charge should be 0. So see, this was the charge which was present with with the mass m. Okay, so this is the mass of it. Q is the charge. Now we here in this is a positive charge. Okay, here the electric field and the forces are acting. Two things are obviously acting. Electric forces are acting and electric forces are giving rise to electric field. This is what is the scenario. Now we want to calculate the magnitude and direction of electric field. See, this is basically this charge was present and this was falling in air. So what happens here when this charge is falling? Downwards you have mg acting of this charge. So see, if we have it's a positive charge, so the direction of electric field, see, if we have to make this in equilibrium and not let it fall down, we should apply a force in which direction?
Um,
Which?
Ma'am, force. But then there's an electric field, right? How do you apply force?
See, a charge is falling down with the force mg.
Ah,
Which direction you should apply one more force so that this does not fall?
normal towards the top.
Upwards. Upwards. Why
Upwards,
do you use
upwards.
such heavy terms? Up, down, right, left. These are enough. You can use these.
Oh.
So there should be a force upwards. That is, the
Mm,
electric force should act upwards, then only this will be in equilibrium. So if
mm,
electric force has to act upwards, direction of electric field will also be upwards because it's a positive charge. So we can say F is equal to QE and F is equal to mg. So when you equate QE is equal to mg, electric field is mg divided by q. This is the magnitude of electric field and the direction will be upwards. Got it? Please
yes,
write it.
ma'am.
Basmi, you write it. I'm coming in 5 minutes. I have to offer namaz here. It's Maghrib time over here. Okay, and I think long back Azan was then. Okay, I'm just
Okay.
coming in 5 minutes. Okay.
Okay, ma'am.
Yeah, Basmi, you there?
Yes, ma'am.
Okay. Done, written?
Yes, ma'am.
All right. Okay. I think this will be the last question from this topic. See, this is a little modification of that topic. This says a particle Q enters a region of electric field E with the velocity V. Length of the plate is given as L. Now it is saying, what's the time taken by the particle to cross the plates? And you have to tell the deflection of the plate. See, time taken one we have done. This time taken part we have done. A Q is charge is there. If a positive charge is there, we are trying to move it. When you are trying to move it, what will happen? See, initially the charge will try its best to move like this. It will move like this. But see, because of the negative charges that are present, this isn't likely to be present and move in a parallel plate manner like this. It means parallelly to this plate, because it is repelled by this positive and it is being attracted. So eventually what will happen? It will move like this and it will go. So this deflection means this separation means what's the deflection? Original path was this and it is now like this. So what's this deflection? This is what the second part is saying. See, in this question, if you see, this is not motion in a straight line. In the previous case, we just had motion in a straight line. Right now, we have motion in a plane. Can you see X and Y? Both the coordinates are changing. If I draw this properly, see, this would be something like this. Can you see both X and Y coordinates are changing?
Yes, ma'am.
So this is not a question of motion in a straight line. It's a question of motion in a plane. And whenever you have motion in a plane, you solve things separately across x-axis and y-axis. So what you do here, for x-axis first we will see. See, length of the plate has been mentioned as L. So x is our distance is L. Now, is there any acceleration along x-axis?
Oh, no.
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 And an acceleration along y-axis?
Yeah.
Why?
Isn't it going upwards?
Because it is going upwards.
Actually, I don't think there is acceleration at all.
Sorry, can you repeat?
There's no acceleration in x and y axis.
See, when you're talking about x and y axis, along x axis, there is motion, but that part is right. The body is now moving a little upwards, but it is covering some x-axis distance also. No, there is a distance along x-axis also. Reason is that along y-axis, your gravitation acceleration due to gravity plays a role, which brings it up. Just this, I'm telling you, it's not a question from your only electrostatics. It's a question from your motion in a plane. So you have to solve the way you have been solving questions from motion in a plane. Whenever you have acceleration, see, the particle is actually not covering this distance. So this point is right. But why is the acceleration along y-axis? Because of acceleration due to gravity. Okay, so if there isn't any acceleration here, there won't be any force. So let's use the equation. S is equal to ut plus half at square. Now this time acceleration is not given, right? So this part will be 0. X is equal to L. We have the velocity. It said with the velocity V. Means our initial velocity is also given as Vt. So what's the time? Time is L by...
L by.
Yes, that's the first part. But second part says for this deflection, you need to see, for the first part, we were seeing everything along x-axis. Why? Because when we solve everything along x-axis, acceleration gets eliminated and it's very easy to calculate time. But now for calculation of this deflection, you should not use x-axis. X-axis will give you this distance. Now you require this deflection that is along y-axis. So that's why we'll now write everything motion along y-axis. So see, your acceleration will be there. Now, because the electric force is present, it is getting attracted. Along x-axis, nothing was happening. Along y-axis, you have QE by m. And what did I tell you? In motion in a plane, we used to, in motion in a straight line, we used to write this as acceleration due to gravity. But right now, it's a charge is present, electric field is present. So if electric fields are present, charge is there. So directly the acceleration is what we studied. Time, you can write it from here. You've calculated the time will be the same. You just need y, right? And see,
Yes,
the
ma'am.
particle is going along y-axis and it is exiting the plate. The particle will exit the plate straight away. Now there isn't any initial velocity required here, right? Initial velocity was
Yes.
along the x-axis. So straight away, you can write the equation S is equal to ut plus half at square. So this part will be 0 this time. Y will be half. Acceleration is QE by m t square. That is L by V whole square. So y is equal to half QE by m L square by t square. This is the answer. Got it?
Yes, ma'am.
Mark this question important. Okay, this question is important. This question has come a lot in the exams with some modification. Sometimes this angle theta can be asked, anything can be asked from this. So if you have a good practice of the base, you can handle all these things. Please write it.
Okay, ma'am. Ma'am, can you scroll down? Can you scroll down? Now I'm done.
Completed?
Yes, ma'am.
Okay, see this torque part we have already completed. So this completes with a force of charge particle in external electric field. Now, see, we are left with very less amount of topics. Okay, very few topics are there. First is your electric field lines. This has to be covered. And see, I'll just tell you a brief of electric field. Electric field is basically when you have electric field lines, they are just representation of electric field. Okay, how you are
Okay.
representing the electric field. So the properties will take the next class only, and we'll discuss it in the next class, but I'm just giving you an idea. You already know electric field. Few properties are there that we'll discuss in the class. After that, then we are left with electric flux, which has Gauss